Welcome my friends, welcome to my next lecture. Now in my last lecture I talked about the kind of notions of limit, a couple of examples I have discussed, and then I said that if I have a functions f, complex valued functions, and if it is of the form u plus ib, then there is a relations between the existence of limit of f and existence of the limit of u and v. So now, and also I have discussed what is called extended complex plane, and then I promised that there is a connections with the extended complex plane and the Riemann sphere. So my plan is for this talk to talk about these connections. That means how a point in a sphere is connected with a point in the extended complex plane, and then I will talk about the notions of continuity. Okay, so as I said, so today I'll start with the kind of connections with the point in sphere and point in the complex plane. So this is I have written. So this is Riemann sphere and what is called stereographic projections. Now this picture is very important. So what you can do first, you think about you have a plane, complex plane. This is complex plane, right? And then what you do, suppose you have a sphere, and suppose you cut your sphere along the equator via complex plane. So think about that. So you have a sphere, okay, and you have a complex plane. So take a paper, okay. So A4 paper, and suppose you have a sphere, and you cut that sphere with that A4 paper along the equator. Okay, if you do that, think about that picture. Once I have that picture in my mind, then there is a connections. What is that connections? Look, the first point. You say that now once I have a sphere, so it will have a north pole and it will have a south pole, right? So just first note that n. So I have written here n. N stands for what is called north pole. Okay. So now what I am doing is that join the north pole. What is the coordinate of the north pole? So if I have a 3 dimensions, it is nothing but 0, 0, 1. Then what I am doing is that, so you just always imagine that picture you have in your mind, like you have a sphere and you have a like plain paper which think about as a complex plane, and you cut it through the equator. Okay, then what I am doing is that, so I am joining my north pole with a complex number z by a straight line L, and which should pierce the sphere, or which should cut the sphere at the point capital Z. So okay, for example, so this is my complex plane. Again I am extending it. Okay, so this is my complex plane. Okay, and so this is my equator. So this is my equator. So that means you will see that this is if I have a sphere of say unit radius. Okay, so therefore equator is nothing but like modulus of z is 1. You can think about it in this way, or x square plus y square is equal to 1. That equator. Okay, the circle. Okay, circle. So therefore you have a sphere in 3 dimensions, right? Then you have a xy plane. You cut it in the middle, and suppose in the middle you have a, then if I have a plane and if I have a sphere, if I cut it, you will have what is called circle, and the equation of the circle is x square plus y square is equal to 1, and that is known as the equator. Okay, so then what I am doing is that in the sphere you just fix the north pole, and suppose you have a point z in the what is called complex plane. Then what you do, you have a complex plane, a point in the complex plane, you have a north pole. Then what you do, you just draw a line, or make a line, joining line from the complex number to the north pole. Then what will happen, it will cut your sphere at one point, and that point I am denoting as capital Z, and that exactly I have written. Okay, so that is the point from here. You can say that, okay, if I take a point for here, point here, then what will happen? Then you can just draw a line, okay, and it will cut your sphere here. Okay, so therefore whatever point I can take in the complex plane, if I join with the north pole, it will always cut your sphere at some point, and I am denoting that point is capital Z. Second conclusion is that the mapping Z goes to capital Z gives an 1-1 correspondence between what? Between the sphere minus the north pole, because I am not associating a point corresponding to north pole. I am saying that take a point in the complex plane and you just associate it, or you just draw a line with that north pole. Then what will happen? It will cut a sphere at some point. So therefore, if I take out the north pole from the sphere, it will have a 1-1 correspondence with the point in the complex plane. So that is it is quite clear from the picture, because if I take a point here and if I draw a line with the north pole, then you see this is the corresponding point in the sphere. If I take a point here and if I have a north pole, if I draw a line, it will the corresponding point in the sphere is this one. So therefore whatever complex number I can take in the complex plane, and if I have a north pole of the sphere and if I draw a line, it will always cut your sphere at some point, and then you will have a 1-1 corresponding with the complex plane, and then not the full sphere but sphere minus the north pole. So that's exactly how I have written 1-1 correspondence. Third observation is that now I have extended complex plane. Now if mod, now look, this is very one observation. So now if I have a z here, so suppose this is my origin, right? So distance between this point to this point and distance between this point to this point is big. So therefore if I take a point here, okay, so then I can draw a line with the north pole. You see the cutting point is here. If I take a point here, so it will intersect your sphere here. If I take a point here, then it will intersect here. If I take a point here, so that means if I take a complex number which is far away from origin, then the corresponding intersecting point approaches to north pole. For example, if I consider the point complex plane here, it will cut the sphere this point. If I take a point here, it will cut the sphere here. If I take a point here, it will cut the sphere. If I take a point here, then it will cut the sphere here. So therefore, if your complex number, absolute of the complex number, is very large, then if it is very far away from origin, the corresponding intersecting point in the sphere approaches to the north pole. So therefore, it is expected I should include a point at infinity in the complex plane with the kind of point north pole. Okay, so that's exactly I have written. So therefore, as mod z approaches to infinity along any direction, that is very important. So I am considering complex number here. You can do the same kind of conclusion here also. So if I have a point here, okay, so if I draw a line, it will cut here. If I take a point here and if I draw a line, it will cut here. If I take a point here and if I draw a line, it will cut here. So therefore, whatever directions I can take, as long as my modulus of z is approaches to infinity, that means away from the origin, and if I join a line from the north pole to that point, that means that intersecting point in the sphere approaches to the north pole. So therefore, what I am doing is that, so because of these observations, my last kind of fourth conclusion is that associate the north pole with the point at infinity. So now, earlier I have a like 1-1 correspondence with the complex plane and the point in the sphere minus north pole. So only north pole is remaining. So now what I am doing, because of this kind of properties, I am associating north pole with point at infinity. Then you see there are nice things are going on. So for example, if mod z is greater than 1, that means if say z is like, so this is actually z is equal to 1, okay, or x square plus y square is equal to 1, or mod z is 1, okay. So if I take a point here z which is modulus of z is greater than 1, that means you see if I draw a line with the north pole, it is always cut the sphere in the upper half plane. That means it is actually the upper hemisphere, okay. Now if I take a complex number z which is mod z is less than 1, that means if I take a point here, okay, somewhere here, that means it will always cut the sphere here itself. That means it will cut a point in the lower hemisphere. And the point mod z is equal to 1, this is exactly the equator. So that's exactly I have written. So mod z is greater than 1, which maps to upper hemisphere. Mod z is less than 1, which is the lower hemisphere, and mod z is exactly equal to 1. This is actually the what is called equator of base. So if I have this kind of things, then I will have one or I should say that bijective correspondence between the sphere and the extended complex plane, not the complex plane. Complex plane has a 1-1 corresponding 1-to-1 correspondence from the sphere minus north pole. But the properties I have observed, if I associate north pole with point at infinity, then I will have a bijective correspondence between the sphere and the extended complex plane. So then the last conclusion is that the corresponding sphere is called the Riemann sphere, and the bijections between the sphere and the extended complex plane via this projection. So this is a projection, like if I draw a line from n to the complex, any point in the complex plane, it will cut. So this is the map. This is called the what is called the stereographic projections. Okay, so therefore this is very nice. So a point in the extended complex plane and a sphere, there is a 1-1 correspondence, where north pole is associated with the point at infinity, and if I take any point in the complex plane, if modulus of z is greater than 1, then it associate a point in the upper hemisphere. If modulus of z is less than 1, then it associate with the point in the lower hemisphere. And if mod z is exactly equal to 1, which is nothing but the point in the equator of the sphere. And that's how it gives the bijections. That sphere is known as Riemann sphere, and the corresponding identifications, the point in the complex plane and point in the sphere, it is called the what is called stereographic projections via the joining a line through the north pole. Okay, so now once I have extended complex space and point at infinity, so therefore it is natural to talk about the existence of limit at point at infinity. That means you can have this kind of limit z approaches to infinity f of z, something like that. Is there any kind of meaning? Answer is yes, you can do that. Okay, so let f be a functions from D subset of C to C, and suppose z naught is a limit point of D. Then first look, this is the symbol. So what is the symbol? I am saying that limit z approaches to z naught f of z is exactly equal to infinity. That means what? If z approaches to z naught, then I am saying that my value of function f of z is equal to infinity. That means what? Absolute of f of z should blow up. That means it should approaches to infinity. That's what it says. So what is the meaning or epsilon delta definitions? So given epsilon, I should have a delta such that if z approaches to z naught, that means if I take a z a point in the deleted neighborhood of z naught, then my functional value, that means the value of f at z absolute, should blow up. That means given epsilon, if there exists a delta such that if I take z from the deleted neighborhood of z naught, then my functional value f of z should be greater than 1 by, because it should blow up, now it should very big. So if I choose epsilon is small, 1 by epsilon is very large. So that's the meaning of limit z approaches to infinity, f of z is equal to infinity. What will happen now? This is again I have a function f from some domain D subset of C to C, and suppose infinity is a limit point, then what is the meaning of this object? This is the meaning, means z approaches to infinity, that means modulus of z approaches to infinity, then what will happen my functional value? If I say that f of z approaches to w naught, then I am saying that if z approaches to z naught, then functional value approaches to w naught. What is the meaning? Again epsilon delta. So this time what will happen? Given epsilon, I should have a delta such that you see z approaches to infinity, that means z should be very large. That means there should exist a delta if mod z is greater than 1 by delta. Now if delta is very small, 1 by delta is very large. So therefore if mod z is very large, given epsilon very small, the distance between fz minus w naught should be very small. So that means I am saying that if modulus of z is taking larger and larger value, then the value of the functions at z minus w naught should be very small. So therefore given epsilon, I should have a delta such that modulus of z is greater than 1 by delta. That means if modulus of z is very large, then the corresponding difference between fz minus w naught should be very small. Okay, so therefore this is z approaches to z naught, fz is infinity. This is z approaches to infinity, fz is w naught. So one part is remaining, that if limit z approaches to infinity and f of z is equal to infinity, that means z is modulus of z is blow up, and then the corresponding functional value this also blow up. So that means that is also you can think about, given epsilon there should exist a delta such that if modulus of z is greater than 1 by delta, that should implies modulus of f of z should also greater than 1 by epsilon. That means if mod z is large, then I demand that modulus of fz also should be large. So in terms of epsilon delta, of course it is not showing here. The thing is that given epsilon there exists a delta such that if modulus of z is greater than 1 by delta, that means if the modulus of z is very large, then the corresponding value of f of z modulus, this is also very large. That means this is also greater than 1 by epsilon. If these things happen, then I am saying that in the last case it is limit z approaches to infinity, f of z is infinity. In the second last case, limit z approaches to infinity, f of z is equal to w naught. And in the first one, limit z approaches to z naught, f of z is equal to infinity. That is the limit involving point at infinity. Okay, so this is another kind of related results. That means to deal with point at infinity, sometimes the reciprocal, that means 1 by z. If z approaches to infinity, what does it mean? That means modulus of z approaches to infinity, that means what will happen? 1 by mod z. This should approaches to 0. So therefore sometimes to talk about the behavior of my functions at point at infinity, somehow the reciprocal, you would consider the reciprocal and look at the behavior of this reciprocal, whether it is goes to 0 or around the 0, what kind of things is going on. So that is the relations. So for example, limit z approaches to z naught, f of z is equal to infinity, that is equivalently limit z approaches to z naught, 1 by fz should go to 0. So if 1 by f of z should go to 0, that means f of z should blow up. That means f of z limit should be infinity. Similarly, second, limit z approaches to infinity, f of z is equal to w naught. That means z approaches to infinity means what? 1 by z approaches to 0. So therefore I would like to see what is the behavior of my functions f at 1 by z. So it says that yes, limit z approaches to infinity f of z is equal to w naught if and only if limit z approaches to 0 f of 1 by z should be the value is equal to w naught. And third one is that if both of them infinity, that means z is also approaching to infinity, f of z is also approaching to infinity. That means if I transfer to the behavior around the point origin, that means if z approaches to 0, then of course f of z behavior, that means 1 by f of z should be there, and at the same time z approaches to infinity, then it should be 1 by f of 1 by z. So therefore this is the kind of independent variable. So independent variable approaches to infinity, that means I have to look at the behavior at 0, that means I have to reciprocally, that means 1 by z. And dependent variable means what? F of that, right? So since f of z, which is the dependent one, if it approaches to infinity, that means 1 by fz I should consider, but z also approaches to infinity, that means it should be 1 by f of 1 by z. Okay, so these are equivalent. So what I'm trying to say is that, so look at the, so to conclude the behavior of your functions or the point at infinity, it is if and only to look at the behavior of the reciprocal of your functions or reciprocal of the point at 0. So that's what it says. If I have these three informations, this is an exercise, you should complete it, that what will be the corresponding limit here. Now z approaches to infinity, what you can do? You just use that fact. So this is the one. You just replace z to 1 by z and using the value, using the limit z approaches to 0. So for example, if I look at here, so this is same as you can say that using the condition 2, limit z approaches to 0. So this is functions, if I write it as f of z, that means this is f of 1 by z. Okay, what is that? Limit z approaches to f of 1 by z means 4 divided by z square divided by 1 by z minus 1 whole square. What is that? So this is same as limit z approaches to 0. Okay, so this should be 4 by z square, and then you will have a z square divided by 1 minus z whole square, right? So this is get cancelled, so therefore this should be limit z approaches to 0, 4 divided by 1 minus z whole square, and this is nothing but 4. So this limit is 4. Just do that. Okay, so instead of dealing with point at infinity, you just take z to 1 by z and z approaches to 0 and consider the functions f of 1 by z and look at the limit. So that's how you just complete this and this. Okay, so now come back to the kind of notions of continuous functions. So as I said, of course these notions you all already familiar with, like real valued functions. Like what is the definitions of continuity for real valued functions? So if you remember, so that means that is the corresponding notation. Limit x approaches to x naught f of x is exactly equal to value of the functions at x naught. So the difference between limit and continuity is that, so for the existence of limit, I do not need my function should be defined at the point x naught. However, to talk about the continuity of f at that point, I need that my function should be defined at the point. Why? Because two things I need. First, the existence of limit at the point x naught of my functions. Not only that, whatever the limiting value will be there, and that should exactly equal to the value of the functions at that point. So therefore, this is important. So therefore, so same thing, like whatever the concept you know the continuity in real valued functions, I can like typically extend in the context of complex valued functions. Just the corresponding real modulus should be replaced by the complex modulus. That's it. So okay, this is my definitions. Let fz be a complex functions of complex variable z that is defined for all values of z in some neighborhood of z naught. You see, I'm neighborhood of z naught. Then I am saying that f is continuous at z naught if for each epsilon there exists a delta. So whenever z belongs to the delta neighborhood of z naught, my functional value should be belongs to the epsilon neighborhood of f of z naught. So therefore, if distance between z and z naught is very small, then the distance between f of z and f of z naught should be very small. So therefore, if b delta of z naught, this should implies f of z be epsilon of f of z naught. Okay. So therefore, if z approaches to z naught, then the corresponding my functional value should approaches to a value, and that value should be exactly equal to the value of the functions at z naught. If that is the case, then I am saying that my function is continuous at the point z naught. So it is nothing but the same thing about the limit, but this time I need or I demand that the limiting value should be the value of the functions at that point z naught, where I am talking about the continuity of my functions f. Okay, so equivalently, f is continuous at the point z naught if this limit exists. As I said, this is the limit I am talking about, and the value of the limit should be exactly equal to the value of the functions at the point z naught. Okay. there is one definition. So if I have a function f from D subset of C to C, so this is actually continuity at a point. So I'll say that my function is continuous on a domain if my function is continuous on a set or domain if it is continuous at each point of my domain. So that's the definitions. Okay, natural questions. So now if I have a complex valued functions, so now I can break up into u plus ib, that means real part of f and imaginary part of f. What can I say about the continuity of these functions u and v? So if I know the continuity of functions from R2 to R or R2 to R valued functions or real valued functions of real variable to real variables, then is there any connections? I will discuss that. Yes, there is a connections. Okay, so again geometrically like in the limit case, so to be continuous at the point z0, I am saying that function should map nearby points of z0 to nearby points of f of z0. That means if z approaches to z0, my functional value should be approaches to z0. Nearby I am meaning actually in terms of neighborhood, or this is the explanation I already talked about in the context of limit. It says that the continuity of f at the point z0 can be interpreted geometrically. How geometrically? Again, you can think about this is my z plane and this is my w plane. Suppose I have a z0 and the corresponding value is f of z0. Then what is the definition of epsilon delta definition says? It says that if I consider epsilon neighborhood of the point f of z0, then I should have a delta neighborhood, I should have a delta such that delta neighborhood of z0, if I have a delta neighborhood of z0, then the functional value of f of this delta neighborhood of z0 should fully contain in the epsilon neighborhood of f of z0. That exactly I am saying. Okay, so each epsilon neighborhood of z0, which is nothing but b suffix epsilon f of z0, of the point f of z0 in the w plane, this is in the w plane, then there exists a delta. And if I consider the delta neighborhood of z0, then in the z plane, then the value of the functions that maps f of b of delta z0 should inside. That means f of b of delta of z0 should fully contain in b of epsilon of f of z0, like in the limiting case. Okay. Fine. Again, couple of examples I have given. So for example, if I consider the limit using the epsilon delta definition, it turns out that this is the value of the functions at 1 plus 2i. So therefore, my function is continuous. Now look this example. Now this example I already talked about. Like, so for example, what is the limit? Now if you remember, this limit does not exist. So now since this limit does not exist, so therefore my function is continuous. So to talk about the continuity, two things is kind of happening. One, first limit should exist, and not only that, the value of the limit should be the value of the function at that point. If these two things happen, then I am saying that my function is continuous. Here to talk about the continuity of these functions, if I consider the existence of limit, the limit does not exist. So therefore my function is not continuous. Similarly, this you can check, take it as an exercise. If I consider these functions f of z real z divided by modulus of 1 plus z, if z is non-zero and f of z is equal to 1, you see I need that earlier to talk about the existence of limit, you do not have to define f of 0 at some value. But to talk about the continuity, whether limit exists or doesn't exist, that's a different part. But I need the function should be defined at that point if I want to talk about the existence of continuity at that point. So that means that is why I'm defining it. F of 0 is 1 and f of 0 is 1. And then I will talk about the continuity of f at that point. So this is already I have done it. The limit does not exist, so therefore my function is not continuous. You just check of this example. Same way it says that the function is not continuous. Okay, so well here I already kind of said that you have to prove it. Okay, is that limit z approaches to this time, what will happen? Limit exists. In this example, limit does not exist, so therefore my function is not continuous. This time what is going on? Limit exists, but what is the value of the functions at 0? This is 1. And what is the limiting value? 0, which is not is equal to f of 0 is 1, so therefore my function is not continuous. Now if I define f of 0 is equal to 0, then my function is continuous. Okay, so these two examples differs that first example limit does not exist, so therefore my function is not continuous. Second example, limit exists, and what is the limiting value? 0. Now if I define my function f of 0 is 1, that means it is not exactly equal to the value of the limit, so therefore my function is not continuous. However, if I define f of 0 is equal to 0, then my function is continuous because limit exists and limit is exactly equal to the value of the functions at 0. Okay, so this is again some algebra of continuity, like this kind of properties you are familiar with of real valued functions of real variable. So Okay, so this theorem, as I said, so like if I have a complex valued function of complex variable, and if I write it of the form u plus ib, what can I say about the continuity of f, and what kind of effect it will be on u and v? And if I assume that u and v are continuous, can I talk about the continuity of f? Answer is yes. Look, this is the theorem. So let f of z, which is u plus ib, is defined in a neighborhood of z naught, then f is continuous at the point z naught if and only corresponding u and v are continuous at the point x naught comma y naught. The real part of f and imaginary part of f, these are also continuous functions. So like in the limit I said, you can easily prove that theorem. Similarly for the continuity, you can also prove it. Okay, so it is very nice. So it says that if I have a function f, complex valued functions, if it is continuous at the point z naught, and if I write my functions f of the form u plus iv, then I am saying that the corresponding functions u and v, which is a map from R to R, this u and v are also continuous functions at the point x naught comma y naught, and also vice versa. If small u and small v, if they are continuous at the point x naught comma y naught, then the corresponding functions f, which is u plus iv, that is also continuous at the point z naught. So I'm not going to prove it in details, but existence of limit, I already said how you do that. You have to just play with the modulus of the complex number, nothing else. Same thing, you just play with the modulus of the complex number and the definition of the continuity. So one continuity, the complex continuity, that means limit z approaches to z naught, f of z is equal to f of z naught. Another continuity, u and v, for real valued functions of two real variables. So from u from R to R and v from R to R. If I use that continuity, then you will be able to prove it. So I am not proving in details, just take it as an exercise and prove it. Okay, so this is the algebra. That means sum of two continuous function is continuous, difference of two continuous function is continuous, product of two continuous function is continuous, and division is a continuous function, provided if I want to say that continuity at the point z naught, that means g of z naught should be non-zero. Okay. One more kind of theorem, it is there. Suppose f is continuous at the point z naught, and suppose g is continuous at the point f of z naught, then I can talk about the continuity of the composition functions. Okay, so that means if I have functions f, if I have function g, and suppose g composed f makes sense. G composed f makes sense means what? That means the range of f should be in the domain of g. So that kind of conditions I need it. Or in other words, if I consider functions f from c to c and g from c to c, then of course g composed f makes sense. Okay, but whenever I am taking say some d1 subset and d2 subset, then one has to be careful so that the range of f should be in the domain of g, and then you have the composition makes sense, and then I can talk about the continuity of the composition functions from the domain of f to complex number. So that's what it says. Suppose if f is a continuous function at z naught, and suppose g is continuous at f of z naught. Now to make sense g composed f, of course g should be defined at the point f of z naught, that is already assumed. So if f is continuous at the point z naught, g is continuous at the point f of z naught, then the composition function g composed f, g which I am writing as g of f of z, it is also a continuous function at the point z naught. So this is another theorem. Again, I am not proving it. Like similar kind of theorem you might have seen in the case of real valued functions of real variable. That means sum of two real valued functions, sum of two continuous real valued functions, they are also continuous. Product, difference, divisions, and also compositions also you have, I think you are familiar with. So similar kind of theorems also true in the context of complex valued functions of complex variable. Last few theorems, again this is, since it is a standard theorem, I am not like proving it. Okay, so like maybe later on, I do not know if I have it, like if time permits, then maybe I'll prove it. But those kind of like theorems you already kind of familiar with in the context of real valued functions. So maybe not the first one, but certainly about the last one. So what is the first one? It says that if f is a continuous function at the point z naught, then modulus of f of z and f z bar both are continuous functions, and that is true. Why? Because you see f of z, okay, write it as g of z. Okay, now what is g? So if f is a function from c to c, and suppose f is continuous at z naught, then what is my function g? So g function is nothing but, you see, these are compositions of mod composed with f. This is the functions, no? Right? So what is that? So therefore g of z, which is this dot f at z, what is that? This is dot of f of z, okay, and what is that? This is modulus of f z. So therefore, G I can think about is nothing but compositions of two functions. One function is f, another function is modulus function. What is modulus function? So z goes to modulus of z. Okay, and you see these functions, it is actually a continuous function. One has to prove. So z goes to modulus of z. So these are continuous functions, and f is continuous at the point z naught is given. Composition of two continuous function is a continuous function. So therefore, modulus of fz is a continuous function. What about f of z bar? Again, same thing. It is a composition of two continuous functions. One is f, another is bar. So therefore, if I consider this function z from c to z bar, so this function you can check that is a continuous function. Okay, and if f is already given to be continuous, so therefore, if I write my function g, which is nothing but f of z bar, which is nothing but you can say that this is bar functions composed with f at z. So this is a continuous function at the point z naught. Z goes to z bar. This is the bar functions you can say. So it is the bar functions. I can denote these are bar functions from c to c, where z goes to z bar. It is a continuous functions, and this is nothing but f of z bar. So this is nothing but f of z bar. So compositions of two continuous functions is a continuous function. So therefore, first theorem is automatic using the properties of continuous functions. These two theorem, as I said, maybe later on I will prove it, but the statement, I think it is quite clear, and of course this kind of statement you are familiar with in the context of real valued functions of real variable. So what it says that let f be a map from some domain D subset of C to C. Now if D is a connected set I already talked about, and if my f is continuous functions on D, then the set fD, that means image of f of D, it is also connected. So that's what I'm saying. Continuous image of a connected set is connected. So I think if you are kind of familiar with this kind of theorem in real valued function, the same theorem is also true for the complex valued functions. So that means continuous image of a connected set is connected. That means if I have a function f from some D subset of C to C which is continuous and D is connected, then f of D is connected. What about the second one? Second one is that continuous image of a compact set is compact. Okay, that is also kind of similar kind of theorem you might have seen in the real valued functions. What it says, so let f be a functions from D subset of C to C, and suppose D is compact. Compact set I have already talked about, like in the real case a compact set definition or whatever either some properties, a compact set is closed and bounded. Similarly in C also it is closed and bounded. So if D is compact, and suppose if my function is continuous in D, then the image set f of D is also a compact set. So that's what I'm saying, continuous image of a compact set is compact. Moreover, modulus of f attains maximum and minimum values. Why? Again also same thing. So modulus f, see if f is a complex valued function, so if z goes to f of z, it is a complex valued function, then z goes to modulus of f of z, that is also a continuous function, but this time this is belongs to R or R plus. So real valued functions, positive real valued functions, continuous functions. And what is the, if the domain you have a compact set, then the range is also compact, and since it is real valued, so therefore it attains maximum and minimum values in D. Okay. So therefore it attains the maximum minimum, that kind of things you know in the real valued functions case. So similarly this kind of theorem also true for complex valued functions of complex variable. Again last two theorems, if time permits then I will prove it, but for the first theorem it is just a consequence of the algebra of continuous functions. That means if I have two continuous functions, just the earlier one I have defined that composition of two continuous function is continuous. From here it follows that modulus of fz and f of z bar, this is also continuous function. Why? Because f is continuous and modulus function is continuous functions. And the second one, f is continuous and bar function z goes to z bar, this is a continuous functions. And f is continuous function, so therefore composition is a continuous function, and therefore f of z bar is a continuous function. Similarly here, fz is continuous functions and z goes to mod z is also a continuous function. So therefore composition of two continuous function is a continuous function. So many way you can do that. So there are kind of very few results of continuity I have discussed. There could be many. Okay. So I think that's very little about the continuity of a complex valued functions. So if you just realize the notions of limit, continuity, So whatever like notions of limit, continuity you know in the context of real valued functions of real variable, you see the parallel concept. In fact, some parallel theorems are there in the in the context of complex valued functions. Just the only difference is that corresponding modulus of the real number should be replaced by the modulus of the complex number. That modulus is well defined. I have defined it. So therefore, the notions of limit and notions of continuity, that's almost parallel, that you are familiar with in the context of real valued functions. So now the next concept is called the differentiability. There you will see there is a difference between like the differentiability from R to R. You know, of course, the definitions you can have it in the corresponding definitions, you can have it in the context of C to C, because R is a field and the complex number is also a field I have talked about. So therefore, you see the definitions you are familiar with in R, the same definitions I can bring it to what is called C. That part is okay. But you see, whenever I talked about f is a complex valued functions, then you will have a representation f is u plus iv, where u and v is a map from R to R, and there is a connections between the existence of limit and continuity of f in terms of u and v. Then the natural question is, you can have the definitions of differentiability, because R is a field, C is a field, the same definition I can give there. Now the question is, there also f is of the form u plus iv, that you can write it. Now can I have the relations with the differentiability of f, complex differentiability? Can I have the relations with the differentiability of u and v? There you will see, no, it is not the case. You need some extra conditions. Not like the existence of limit of u and v implies the existence of limit of f, and continuity of u and v implies the continuity of f. In differentiability, it is not the case. So that means the differentiability of u and v, of course, there you will have R2 to R functions, that means partial derivative will play a role. So then the question is whether the partial derivative, existence of partial derivatives of u and v implies the existence of differentiability of f or complex differentiability, and vice versa. Answer is in general no, and there the major difference you will have it in comparison with the concept of limit and continuity. So now, till now I have discussed limit and continuity. In my next lecture I will talk about the differentiability, where you will see the major changes. And to talk about the differentiability like in terms of u and v, one very fundamental concept will come, that is called Cauchy-Riemann equation or CR equations. So they will see how CR equations is coming into the picture to talk about the differentiability of complex valued functions of complex variable, and what is the relations with the real differentiability. That means if I have a functions, say if I have a functions from C to C, now I can think about C as a set from R2. So same function C to C I can think about as a functions from R2 to R2, because the point in C and point in R2 they are identified, right? So therefore you can ask, so I have a notions of complex differentiability you have discussed. Now I already know the notions of differentiability from R2 valued functions of R2 variable, by functions from R2 to R2. Then the question is, that differentiability, R2 to R2 differentiability, and your kind of definition C2 to C to C differentiability, what is the relations? Can I have any relations? And if that is so, then how it differs and how it connects. So those kind of things will come, and that's how the kind of complex analysis changes from the what is called real analysis. So in my next lecture, I will talk about what is called differentiability of complex valued function, complex variable. I think I should stop here in this lecture. Thank you.